Hello everyone, Assalamualaikum warahmatullahi wabarakatuh and good day to every one of you. Welcome to my video. So in this video, we are going to continue our lesson on chapter 1, which is magnetic circuits. Okay, so my name is Dr. Nur Zulaili binti Muhammad and here is my email address. If you have any question regarding the content of this video, you can just feel free to email me. Okay. Alright, so let's move to the next slide where we are going to see what are the subtopics that we are going to cover in this video. So in this video, we are going to see what is the definition of the magnetic field and how to produce the magnetic field. Okay, and then after that, we are going to see the equations that very important in order to solve the magnetic field problems. Okay, and then after that we are going to go to the next subtopic, which is the magnetization curve, or we can also call it as a BH curve. Okay, so basically for this subtopic we are going to see the relationship between the magnetic field intensity versus magnetic field density. All right. Okay, let's move to the next slide. Okay, so the first subtopic that we are going to cover is a magnetic field. Alright, so how to produce the magnetic field? Consider that you have a simple structure, just like shown in this diagram. Okay, so where you have a magnetic core, this is your magnetic core, with a mean length of LC. So LC represents the mean length of the core. Okay. And then the magnetic core have a cross-sectional area of AC. Okay. And then you have a wire, a coil here, a coil that carry the current of I. Okay. Alright. So whenever you have this, so it will produce the magnetic flux lines across the magnetic core. Alright, so the permeability of the core material we call as a mu C. Okay, so mu, or we can also call as a mu core. We can assume that the size of the device and the operation frequency are such that the displacement current in Maxwell equation are negligible, and that the permeability of the core material is very high, so that all the magnetic flux will be confined within the core. It means that the magnetic flux line will confine within the core. Alright? Okay, so this is how you produce the magnetic field. Okay, next. The relationship between the current I and the magnetic flux intensity H, or we can call as a I-H relation, can be obtained by using the Ampere's law. This law states that the line integral of the magnetic flux intensity H around a closed path is equal to the total current linked by the contour, meaning that if you integrate the H over the over the closed path, which is dl, it will be equal to the number of turn multiplied with the current. Okay, so this represents the total current linked by the contour. Okay, so this equation can also be rewrite as a, if you integrate 1 over dl, so you get LC only. Okay, H you can bring to the outside, so you get H multiplied with LC equal to Ni, okay, equal to F, where your H represent the magnetic field intensity produced by the magnetic core. Okay, LC represent the mean path length of the core, which is in meter, and I represent the magnetomotive force. Okay, or we can represent the Ni equal to F. F is basically the magnetomotive force. Okay, the unit for magnetomotive force is A turns, or you can also call as a ampere turns, or we can write it down as a AT. Alright, and then next, the magnitude of the magnetic field intensity H in the core due to the applied current is given by this equation. So from the previous slide, you can rearrange the equation so that you get H will be equal to Ni, which is your magnetomotive force, divided by your mean length of the core. Alright, so Ni divided by LC. Okay, And then the relationship between the magnetic field intensity H and the resulting magnetic flux density B produced within a material is given by this equation, which is B, magnetic flux density, equal to the mu C multiplied with the magnetic field intensity H. Okay, so the mu C, the permeability of the core is equal to the mu naught multiplied with mu R, where the mu naught is the permeability of the air multiplied with the relative permeability. Alright? Okay, so this is the equation that you need to memorize in order to solve the problem on the magnetic circuits. Alright? Okay. So, H basically represent the magnetic field intensity, where the unit is a ampere turn per meter, AT over meter. Okay, and then the mu C is a magnetic permeability of the material of the core. Okay, so the unit is in terms of henries per meter. And then the B represent the magnetic flux density. Okay, so if H is a intensity, but for B is a density. So the unit for B is a Tesla, or you can also write it down as a Weber per square meter. Alright, and then you also have a mu R here. Mu R represent the relative permeability. Okay, usually this value is given in the question. It can be either maybe 4,000, maybe 2,500 and so on. Alright, so usually the relative permeability will be given in the question. Alright, and then you also have a mu naught. Mu naught is a permeability of the free space, which is 4 pi multiplied with 10 over minus negative 7 Henry per meter. Alright, okay, so this is the constant value that you will need to always remember, then use in your calculation later. Alright. Okay, therefore, the magnetic flux density B for the magnetic core is given by, because you know B will be equal to mu C multiplied with H, okay, and then you also know that your H, which is your magnetic flux intensity, is equal to magnetomotive force divided by your LC, so that's why you can integrate into this equation. So your B will be equal to mu C multiplied with N, your turns, multiplied with your I, which is your current, divided by your LC. LC is the mean core of the, mean length of your core. Okay. Now the total flux in a given area is given by, total flux will be equal to the B, which is your magnetic flux density, multiplied with your A. A is a cross-sectional area. Okay. So depends. If you want to calculate the total flux going through the core, then you need to use the cross-sectional area of the core. If let's say the question asking you to measure the total flux of the air gap, then you need to substitute with the value of cross-sectional area of the air gap. Alright, okay, and then we will see in details in the example later. Alright, so A represent the cross-sectional area of the core, or maybe of the air gap, or it depends on your magnetic circuit. Alright, okay, so the total flux in the core due to the current I in the winding is given by, okay, so you know your phi, which is your total flux, equal to B multiplied with A, okay, and then from here you know your B is given by mu C multiplied with Ni divided by LC, so you just substitute here, okay, and then after that you know that you can just bring your mu C and A to the bottom, so you get Ni divided by LC divided by mu C multiplied with A. Alright, so this thing is actually represent the capital letter of R. Okay, so this one considered as the magnetic reluctance. Okay, so Ni is represent the magnetomotive force. Okay, so if we take the magnetic flux, this magnetic flux is as a current. Okay, and then if we take the magnetomotive force F as the EMF of the voltage source, okay, and then if you take your capital letter of R, known as the magnetic reluctance, to become resistance in the magnetic circuit, so you can have an analog of Ohm's law in the electrical circuit theory, where in the Ohm's law you have a V equal to, I will be equal to V divided by R. So here I represent by the flux, and then V represent by the F, divided by R is represented by the capital letter of R. Alright? Okay. And then what is the core reluctance actually? So in this slide, we learn about the core reluctance, or we can also call it as a magnetic reluctance. So in this slide, we are going to see what is the core reluctance actually. Okay, so each core, especially for the ferromagnetic material, has its own reluctance. Okay, what is reluctance actually? Reluctance is actually the opposite of permeability. Okay, so the magnetic property of the core can be improved by using the material that has a very low reluctance, meaning that if you want to have a very good magnetic core, so you must choose the property that has a very low reluctance and very high permeability. Okay, the reluctance of the core is given by this equation. So the reluctance is equal to LC, the mean length of the core, divided by the mu C multiplied with A. Okay, so the mu C is the permeability of the core multiplied with the cross-sectional of the core. Okay, so the reluctance in the magnetic circuit obey the same rule as the resistance in an electrical circuit. So, so the reluctance can be either in series or it can be also in parallel. Okay, so for series, the reluctance equivalent will be equal to the reluctance number 1 plus reluctance number 2 plus reluctance number 3 ... until n. Alright, same goes to the reluctance equivalent for the parallel circuit. You can also apply the same rule as per resistance in the electric circuit. Alright. Okay, next we go to the next subtopic, which is the magnetization curve. Okay, so in this topic, we are going to see the relationship between the flux density, which is B, versus the flux intensity, which is H. So the relationship between the B and H of any magnetic material can be generally shown by this figure. Alright, so this curve we call as a magnetization curve. Okay, alright, so in the core, when you apply the current, when you try to increase the current, it will proportionally increase the magnetic intensity, meaning that when you try to increase the current, the H also will be increased proportionally. Alright, and then from the BH curve, we can see that whenever you increase the flux intensity H, the flux density also will be increased. Okay, and then the increment of the B will be almost linearly. Okay, so whenever you increase the H, the B also will be increased. Okay, almost linearly until it achieves certain condition. Alright, however, whenever the H become more higher, the change of the B is become nonlinear and show the effect of saturation. Here is where we call it as a saturation area. Here is a linear area, and here is we call it as a knee. Okay, the knee area. So the curve is also known as the BH curve, where the slope of the curve is given by mu. Mu, the permeability, is also equal to B divided by H. So just take note that mu will change if the B and H is changed. If you want the mu to be proportional to the F, we need to make sure the circuit is operated at the linear or unsaturated region. Okay, so we must make sure the circuit operated here. Okay, and then to operate with the maximum flux, machine must work within the knee region. Okay, in order to get the maximum flux, we must consider our machine to operate in this area. Okay, so we must avoid our magnetic material to be operated in the saturated area. Alright. Okay, so basically in this BH curve, it represents the curve for various metals, where you have a BH curve for steel is here, and then this is the BH curve for iron, and this is the BH curve for air. Alright, so as you might see, the air have a lower permeability compared to the iron, and then iron also have a lower permeability compared to the steel. Okay, and then the level of the magnetic saturation also different, depends on the value of the permeability of that particular material. Alright, okay, I think that's all for now. I'll see you in my next video. Okay, bye.